Good afternoon, everyone. So today I'm very excited to share with you a technological breakthrough that we've recently achieved here at DUG. Now, on the top left of this slide is a result of a conventional seismic processing and imaging workflow. And it's a really good result, but it took around 9 months to produce. On the bottom left is a result of a completely new approach using a technology called full waveform inversion. And we achieved this result in about 4 weeks using 20 times less man time. Now, it uses more compute, but that's not a problem for us because of our high performance computing ability. That's something we're very good at. Now, these results might look quite similar, but actually the one on the bottom left is much better, and I'll be showing you why in this presentation. But first, I'll explain what seismic processing and imaging is and why it's important. So it starts with the acquisition of seismic data. And this is performed typically by a seismic source generating sound waves which travel through the Earth's surface and reflect back to a set of recording devices. And this generates seismic traces that form our field data. So these wiggles that you can see here on the left-hand side, these represent the recorded sound waves. Now, our job is to turn these recordings into a three-dimensional data cube, which we can analyze to understand the rock structures deep into the Earth. This is an example of the kind of result that we aim to generate. So here I'm showing slices through this seismic cube, and the white and black lines represent different layers of rocks. And geologists use this data to map the subsurface geology and decide on the optimal location to drill a well. Now, it's important that these cubes are as detailed and accurate as possible because drilling a well can cost anything from 50 to 250 million US dollars. So getting the drilling decision wrong can, of course, be a very costly mistake. Now, what we typically do for ease of viewing is to take sections through these cubes, which we can see here, and lay them flat on the page to give vertical slices and horizontal slices. Now, this data set is from offshore Australia, 100 kilometers northwest of Barrow Island. And the white line at the top is the seabed, which is about 1.5 kilometers below the sea surface. And we can see lots of layers of rock all the way down to 4 kilometers of depth in this example. On the bottom, we have an aerial view, a horizontal slice of this data, which is at a depth of around 3 kilometers. And we're going to see a lot more of this data in the upcoming slides. Now, to get from the field data, those wiggles that we saw earlier, to the final result can be quite a lengthy process. The conventional seismic processing and imaging workflow contains many steps, which are shown here. And each of these steps contains many sub-steps. And each of those contain many parameters that need to be tested and applied. And so this can add up to a project taking many months or even years, depending on its size and complexity. It's a very labor-intensive process to come up with the optimal set of parameters. One of the key steps in the conventional workflow is model building, which is where full waveform inversion is traditionally applied. Now, it's at this stage that we determine some key properties of the subsurface to aid the generation of the final result. Just to quickly describe FWI, in essence, it's a fairly simple process. We begin with some initial guesses about the properties of the Earth, which we call models. We then run a huge three-dimensional numerical simulation using our high-performance computing to create synthetic seismic field data. We compare that synthetic data to the real data, and we use the difference to update our models. And then we iterate around, running the same process dozens or maybe hundreds of times. And the result is a set of high-resolution models, which we can then use in the conventional workflow. This is an example of using FWI in the conventional workflow to generate a velocity model of the subsurface. And this is a key parameter to establish in order to create an accurate final data cube. So this data is from Norwegian North Sea. It's got a water depth of around 200 meters. And this is our initial model, which is in color here. And it's co-rendered with the seismic data cube, which is in black and white. So this is a combination of two different data sets. On the left is an aerial view, and on the right-hand side is a cross-section. Now, this is the result after we've run FWI. So we can see that the velocity model that's in color has changed dramatically, again, as we go from the initial model that we started with to after many, many dozens of iterations of FWI. There's a lot more detail that's introduced that ties in nicely with the structures that we observe from the seismic data, which is in black and white. Now, this increase in detail is particularly noticeable on the aerial slice view on the left-hand side. Again, if we can compare the initial model, which is fairly plain, to a very detailed FWI model. Now, this is an example of an onshore seismic data set from Oman. On the left is the initial velocity model, again in color, co-rendered with the seismic, which is in black and white. And on the right is the result after FWI. And again, we see a lot more detail, a lot of changes in the velocity model, and all of these changes conform to those black and white lines which represent the geology. But we also see simplification of the seismic data in the shallow section on the right-hand side after using the velocity model derived from the FWI. And this is expected, and this means that we've generated an accurate and detailed velocity model. Now, what I've shown here so far is the conventional way to use FWI. But the breakthrough that we've made is to use FWI in the conventional manner for model building, but to additionally use it to replace all of the other steps in the conventional workflow. And this allows us to derive a seismic cube directly from the field data without the need for all the above steps and their sub-steps. So doing so removes many of the lengthy and labor-intensive processes that slow a project down, and means that we can drastically reduce the turnaround time. And we're talking here about a reduction from many months to just a few weeks. So let's have a look at some results of this new approach. First, we'll look at the results from a conventional workflow, which is here. These are sections through the same data from offshore Australia that we saw earlier. Now let's look at the FWI result, which is here. Now I'm going to toggle between these two slowly. And as we toggle, we can see that in general, they look perhaps pretty similar. But this is remarkable in itself because the conventional workflow shown here has had a number of processing steps, as we can see on the left, to remove parts of the data that would otherwise degrade the conventional result. But this new FWI approach, which is here, has none of these processes applied. It's taken the raw data and generated a comparable result in a fraction of the time. But in fact, it's a better result than the conventional workflow here. Let's have a look in a little bit more detail. So this is a horizontal slice through the same cube generated in the conventional manner. This is essentially a bird's eye view of the geology at 2.7 kilometers depth. And so what we can see here are a number of features which include rapid changes in geology on the left-hand side, and these are associated with geological faults. And on the right-hand side, hints of a channel system, and these are ancient buried rivers. And so this is the conventional result, as we said earlier, and here is the result from FWI. And now I'll toggle between these, and what we can see initially is that the FWI result is a lot crisper with much more resolution. But we can also see details now that were previously obscured. The channel system on this right-hand side here is now much more obvious and easier to interpret on this FWI image compared to this conventional result. And these kind of details are absolutely crucial when geologists are deciding where to drill a well. I mean, these decisions are ones that could cost hundreds of millions of dollars. Now let's zoom into a shallow area. And here we can see the seabed at about 1.3 kilometers of depth, and we're looking at structures down to 1.9 kilometers. On the right is an aerial slice at a depth of 1.5 kilometers. Again, this is the conventional result, and this is the FWI result. And here we can clearly see the drastic increase in resolution using the FWI approach, particularly noticeable on the slice section on the right-hand side, going from a very blurred image and bringing that into focus thanks to FWI. Again, much more detail and much easier to interpret as a result. So the outputs from the conventional workflow are typically not restricted to a single data cube. In fact, we also generate a set of cubes called angle stacks. And here's some examples from the conventional workflow of those. Now, analysis of these angle stacks allows us to infer details about the composition of the rock. So it's very important. But we can also generate these from the FWI approach. And here they are from this same data set. And as we toggle between them, we can see that these are very similar to the conventional approach. But in fact, the FWI results are slightly less noisy than the conventional data, which is especially apparent in this region here. Again, as we toggle between the conventional and the FWI approach, you can see slightly less noise, slightly more coherent energy in the FWI result. So we really can achieve everything that the conventional workflow gives us with this revolutionary FWI approach. And now we've tested this technology in a range of geological settings from different parts of the world. It's applicable to shallow and deep water offshore and onshore surveys too. In recent weeks, we've been applying FWI to a data set from the Gulf of Mexico. And the Gulf of Mexico contains many large bodies of salt within the subsurface, which are very interesting from an exploration perspective, but they can also make processing and imaging very difficult. Now, our results so far have proven that the FWI workflow is able to perform exceptionally well in even these circumstances, and this gives us a great confidence that the technology is applicable to even the most challenging environments. And this approach isn't restricted just to oil and gas exploration, it's applicable to any kind of subsurface processing and imaging. Earlier, we saw a huge increase in resolution just under the seabed, and these near surface data cubes are important for the extraction of minerals or engineering projects such as tunneling, pipelines, and wind farm installations. So to promote this technology, we've embarked on a multifaceted global marketing campaign across all of our business lines. Recently, we've presented to a wide range of clients via one-to-one technical sessions. And this slide shows a selection of those clients who we've engaged, which includes Chevron, Shell, Exxon, Woodside, and Equinor. The feedback has been universally positive, and the technology has opened up discussions on a number of exciting opportunities. We've also submitted technical papers to major industry conferences in order to reach a wider audience of industry experts. And this is supported by adverts on social media, linking to a revamped website where interested parties can learn more and get in touch. And we've also produced an 8-page brochure, which will be included as an insert in leading industry magazines. This brochure will also be available on our website for those wishing to learn more. Our clients have recognized the commercial advantages to this technology. Getting results faster allows them to be more reactive and more flexible. And one exciting opportunity that the technology presents is that it's now possible to stream data directly from the acquisition vessel into our data centers in order to produce final products extremely rapidly. But the technology isn't just restricted to new acquisition. The improvement in results we can create here has the potential to yield fresh insights into existing data sets. It's not uncommon for new technology to breathe new life into a prospect by revealing details that were previously hidden. Better results allow for better decision making, which is crucial when such huge investments are dependent upon those choices. So to conclude, we've developed a groundbreaking technology that provides better results in less time than the industry standard workflow. It's built from the ground up for big data on high performance compute. It's available to our clients as software so they can run on their machines, or they can run on our machines, and also available as a service. Before I finish, I'd like to take a moment to thank our incredible R&D team, whose fantastic work has made all of this possible. We're very excited to be at the forefront of this technology and leading the way towards what we believe to be a completely new and revolutionary approach to geophysics. Thank you very much.
Thanks, Tom. Now I'm going to try to get hold of any questions. There are no questions. Ryan Evans, sounds like a no-brainer for potential clients. What are the potential impediments to this being taken up in favour of the incumbent processes? It's a question that we've asked ourselves a great deal of. It's about creating belief. It's about creating complete belief. It's about being able to deliver on time in terms of in line with our promises of short turnaround times if we end up getting a lot of projects coming in at the same time. But it's the key is around belief, I think, and it's you're doing a massive change in the behaviour of a big industry. So we've got to get out there and we've got to work really hard to garner confidence and to get projects in and to do it all over the world so that everybody sees it and is aware of it in different settings. Could we detail any competitors using similar tools? We've applied for patents along the way on a number of aspects of this technology. The patent process is quite secretive in the first year or two. So we are not aware, and maybe I could throw to Tom to answer this. I'll give my answer and then throw to Tom. I'm not aware of anybody else doing this at the moment in the marketplace at all. Everybody is doing the model building, which Tom talked about initially. I'm not aware of anybody offering the full replacement like this in the market. Tom, would you care to have a go at that?
Yeah, nothing to the extent that we're offering. There are FWI-based solutions being offered, but many have some technical limitations or don't supply the full range of outputs that we can. That means that those solutions still require the conventional workflow. So that's, I think, the differentiator for us.
There's no complete replacements at the moment, is there?
Yeah, that's right.
What is your best estimate of the likely current market size in terms of US dollars revenue per annum? So this is another question we've spent quite a lot of time asking ourselves, Ryan. It's really difficult to know. We know that the market used to be 1.8 billion US dollars a number of years ago. That was a McKinsey number. Since then, we've, sorry about the dogs, we're all sitting at home, recovering from COVID. Since then, the market got bigger and then the market shrunk a lot over the last 2 years. And now this year it's come back to life. So, but that's our best guess at it. What percentage of that we can get we'll be working as hard as we can to get the largest percentage of that we can. And we currently haven't had any failed attempts to apply this technology. In other words, so far it's all good. It's a complete replacement. But please don't think I'm saying that our turnover is going to go to 1.8 billion US per annum. I don't think that. We do have some very large competitors who, when they see our results, will be working very hard to dodge our patents and work around it. But we do have a really good, solid lead on them. Thanks, Alan, for your question. Is this for reprocessing or new seismic work or both? It's absolutely for both, but I think we'll get much more work on reprocessing of the existing seismic data than for new work. But it's for both. It will breathe new life into seismic. Generally, seismic is reprocessed 3 or 4 times during the life of the seismic data. And this is one of the things that you did, it was not obvious perhaps, is that there's hundreds and hundreds of decisions are made in the traditional processing sequence. In this new approach, there's only a couple. And that means that it's much more reproducible. It's much less open to human decision-making and beliefs and thoughts about what it should look like. And that in itself is going to bring a lot of reprocessing work, or should. Well, if there's no more questions, I thank everybody, and I'll hand over to Sam for a wrap up. Thanks, Sam.
Thanks, Matt, and thanks, Tom, for a great presentation. I'm Doug's interim CFO. I joined in March, so still learning the ropes. But what I really love about this technology is it seems to play really nicely into our wheelhouse, across the 3 business sectors that we operate here in HPC, services, and software. So I think it's a fantastic addition, and we're really excited about it. So I thank you all for your attendance. And if there's any further questions that you didn't get a chance to ask on the Q&As at today's session, please do email them through to investor@doug.com, and we'll do our best to answer those questions. Thanks for your time. That concludes our presentation.
Bye, everybody.